So, good morning, US, good evening, Europe, also good evening, UAE, if some of you join us already. Today we have another very interesting and innovative talk by two SOM architects and engineers. It's Georgi Petrov and Daniel Inocente. First of all, I would like to say Skidmore, Owings and Merrill SOM is a global architectural planning and engineering firm. Existing for a very long time, was founded in Chicago in the 1930s. And today we have Georgi Petrov, a practicing architect and structural engineer, and Daniel Inocente, a senior designer of SOM with us here. Georgi Petrov is an associate director in the structures group at the New York office of Skidmore, Owings and Merrill, and he works on high-rises, long-span roofs with a specialty in glass and steel structures. He's a leader in pioneering some involvements into design for structures in outer space. He is also a fellow member of the Space Architecture Technical Committee. And he introduced Daniel Inocente, also a member of the Space Architecture Technical Committee. Daniel Inocente is a senior designer with SOM in New York as well. And he previously worked for Gary Partners and Gary Technologies in LA, California, on projects like the Guggenheim Museum in Abu Dhabi and the Battersea development in London. But Daniel also worked at NASA, GPL, as part of a team of designers and scientists. And prior to joining SOM, Daniel worked with HKS Line in Washington, DC on some healthcare projects. And today, Georgi Petrov and Daniel Inocente will present her latest space architecture project, the Moon Village project, that probably you all have seen. It's prominently displayed at the Biennale in Venedig, in Venice, and you will hear a lot more about it now. So thank you for coming. The floor is yours.
Thank you very much for the introduction, Sandra. Let me share my screen. Can you see the screen? We're good? Excellent. So as Sandra said, we're from SOM, Skidmore, Owings and Merrill, and we've had a long history of varied projects. We do all sorts of different types of healthcare, education, public, a lot of airports. And we do have offices all over the world, mainly in New York, Chicago, and San Francisco, but we also do have an office in Dubai, several in China, and in London, in Europe. And primarily, we're famous for our super tall towers. This is a little bit outdated, but at any one point, we have 4 or 5 of the top 15 towers in the world are ours. And not only that, but we've developed the structural systems for super tall towers. So most of the different type of systems, the very first example were done by us, at the very beginning.
There's also a wide range of research initiatives happening throughout SOM. You can see here that we've actually assembled teams, and these are all interconnected offices working on various topics such as computational design and fabrication. And a lot of these are really interesting projects for us to just learn about new processes and new materials, and then learn how to apply that to real architecture. Next. Some examples of studies in manufacturing and new materials are here. What you see on the left is the Amy project. That's a 3D printed module where the idea was to try and create an easily deployable structure that could be self-sufficient, that could harness its own energy, and that could be mobilized to different locations. There's another project, the one you see in the middle. This is a 3D printed barrack. This was an SOM initiative coming from Chicago, together with the US Army Corps, looking at how to 3D print structures. And then on the right, you see a research initiative where they were using robotics to assemble large glass brick units. Next. Can you go next, please?
Yeah.
Oh, no, go ahead, go back. Sorry, there was a lag there. I think this is just to showcase that SOM has been involved in the evolution of how we use digital technologies. Throughout the history of SOM, there's been a lot of interest in not just implementing, but also creating and customizing digital tool sets. And I think SOM was one of the first to actually develop its own CAD software called AES in the 80s. And this has continued to, to take place at SOM at various points in time. Continue. This is an image of some of the computational work that we do for skyscrapers. When I get involved in a project, I typically develop customized tool sets to develop design ideas, but also to extract and to integrate multiple disciplines, including structures. Next. This is another example of that. This is for a tower in China, where we're looking at how to optimize geometry for glass fabrication. Next.
And so over the last, 4 or 5 years, Daniel and I have been trying to sort of harness this long history of capability of SOM and apply it towards, design for structures in outer space. And the project we'll talk today is sort of our first big project of many that we're having now. But this was a collaboration with the European Space Agency and MIT that was organized by SOM. And here, we tried to take the challenge that Jan Werner, the former Director General of the European Space Agency, posed back in 2015, I think, of this new idea of how to go to the moon in a novel way, to take the paradigm and the lessons learned of the International Space Station, where instead of competing, we have a common goal. And if we share a common infrastructure, many different partners can go to space more easily. So taking this idea of collaborating instead of competing in space and basically applying it to the moon. And, he colloquially termed it the Moon Village. And there's been a very reinvigorated and interesting discussion the last few years of how to go to the moon in this better, more collaborative way. I won't go into it. You probably all know that the two poles are sort of the most exciting and interesting places to go. And so this is the southern polar region, with the South Pole is right here at the edge of this big crater, Shackleton. And there's been a lot of research of where the best place is, and we've kind of chosen this one area along the rim of the crater to develop our project. You can see here again, the crater is really deep, and most of the interesting science is down at the bottom of the crater, but it's always permanently shadowed. While at the very rim of it, at the highest points of it, it's actually bits where the sun shines for a large portion of the year. So you do have, an opportunity for generating a lot of energy. And there's also some smaller craters that are a lot more easily accessible that you could do science on this. The idea is that we have probably frozen water and other interesting volatiles hidden there, with both interesting scientifically and interesting because they're a resource. And we looked at the long history of ideas of how to go to the moon, going back to the 50s and 60s. And more excitingly, in the last 4 or 5 years, again, partly spurred by this idea of the Moon Village, and partly that a lot of new and exciting commercial players are entering the field. And we feel that it's finally time where soon we could realize this dream to go back to the moon in a more permanent and sustainable way. And so we looked at several different scales, and we'll talk more about them. So we started with the master planning idea, and the idea that you can lay out a growing settlement, and with this criteria of safety, every bit of your habitat has to have access to other bits of it. So if you lose one part, You can't lose or separate different parts of the habitat. Everything has to be efficient for obvious reasons, and it's easily expandable. And so we looked at very different urban planning ideas, and we settled on this one, this idea of a linear city that was sort of brought forth in the beginning of the Industrial Revolution by the Spanish architect Arturo Soria and made famous by Le Corbusier with his plan for a linear city. And here the idea is that you could have a spine of infrastructure that grows in both directions, that's very efficient in moving materials and humans back and forth. But if you have several bands of it, you could have the safety and interconnectivity and things like that. And so this is sort of a zoom in of the crater rim with a band of habitats all tied together, and then a band of infrastructure where you have all of the outside equipment that needs to support the habitats, and then maybe a band of activities. So if, for example, you have a government agency that's like NASA or ESA that's part of the Moon Village that wants to set up a scientific expedition with rovers, they could have a staging ground, and right next to them, maybe you have a tourist company that is providing a visit to the moon, and maybe part of their experience is having an outdoor space where people could play lunar sports or other research activities. And again, we looked at precedents on Earth. Here you have something very similar at the South Pole Station. You have the sort of the old habitat from the 60s, and then this is the new one that was built a few years ago, sort of lined up together. And then next to it, you have all of the infrastructure and the setup and the layout. But we also looked at not just what you need to survive and the safety, but what does it take to make a human settlement? And then there's this example of another from Antarctica. This is McMurdo Station, where you do have all of the equipment, but it's like a big mess. Everything is growing. There's no sense of identity, no sense of place, and every human settlement, right? You have people living, but you also have these spaces that were designed and provide an iconic image. We have Central Park here in New York, which is instantly recognizable as part of the city and a great amenity. In Vienna, you have the Ringstrasse, which is also instantly recognizable and a big feature of the city. And so we said that besides the engineering, you would need some sort of to leave a place, maybe out along the crater rim in the direction of the Earth, where you would have an undisturbed piece of the moon. So as the humans go around, there's always a bit of undisturbed moon. And we thought we'd place it in the direction of the Earth. And so where you're in the habitats, you always have this view of the undisturbed, pristine, beautiful moonscape, but the Earth is always behind it. And this is actually a cool view. Daniel found this yesterday, even a new animation by NASA that shows that view. This is the rim of the crater, and the sun always travels along the horizon. And because of the moon's orbit, the Earth is always in this direction. It never really strays. It throughout the month and the year, it kind of wobbles, moves up and down around the sky, but it's always in that one direction. It stays like this, spinning around. Sorry. And so we started then zooming in with this master plan idea and laying out the individual habitats and some ideas of how they could grow together and be interconnected. This is sort of an early stage where you have a few of them starting to be accumulated. And then, this is the rendering of what it could look like in a few years, where you have the band of habitats, you have the crater falling down, and then you have the band of infrastructure here, solar panels and things getting assembled. And then the idea that in the future, you're starting to practice and experiment with different types of construction, maybe in situ resource utilization and elements built in from the site. This is another view of the crater rim and how the habitat could grow. And this always this idea that, you know, you're looking back at the Earth, and every habitat has a view back towards it. So next, then we took this master plan idea, and then we looked in detail of what one of the habitats would be, and then Daniel will explain the process there. So going in from the master plan into what the individual habitat is.
So this is a picture of all of us together with the expert team from ISA STech at their facilities in the Netherlands. And this all took place at the CDF immediately after we actually took a trip down to Paris HQ and met with Jean Werner. We presented the concept to him, and as it had been developed, you know, just from a big picture, more from a visionary point of view, not from a technical perspective, but we wanted to, you know, understand both things, you know, big picture, small picture, looking at more details as we started the CDF. If you go to the next image, you can see that the team was made up of a wide range of experts, including power, radiation, structures, systems, thermal, and this was organized and led by Advinit Makaya from STech and also Piero Messina from ISA, and they assembled this expert team. And so we were there with them for a couple days in person, and then afterward we were doing these sessions, these CDF sessions remotely. If you go to the next slide.
Sorry, just to interject. Actually, the architecture and crew accommodation specialist was a student of Sandra's that took the class that you're in, Marlies. So there's that connection as well. Back to you guys.
And so everything started with looking at transportation, since the transportation performance really limited what it was that we were designing. And we started off, you know, just looking at what's available and what's coming near term. And we're all aware of some of the near term transportation systems that are being developed by commercial entities. But then we also have a lot of heritage technologies being used to develop the SLS. And this is one thing that I think the ISA team really wanted to emphasize, was that we had enough information about the SLS that we could use that fairly confident. And so we ended up actually proceeding with looking at the SLS architecture as the mode of transportation for the design that we were coming up with. If you can go to the next slide. And the methodology was to first establish what we were trying to accommodate. We were trying to accommodate a crew between 4 and 6 for a mission duration of around 300 consecutive days. And the habitat had to be deployable. And so that meant that what we were doing was basically designing, engineering, and fabricating the habitat on Earth so that it could be launched, delivered, and prepared on site on the moon, so that it can easily be occupied by the crew once the crew arrives. And all this set the base, you know, kind of like the baseline objectives for how we would approach designing the infrastructure, but also the habitat from a human perspective. If you go to the next slide. The various mission phases that we took a look at included testing, looking at how we would test some of the features in the habitat, because we were designing something that was hybrid in terms of its structure, the launch sequence, looking at how we would take the habitat up into low Earth orbit, what assets we would need to be able to take it from low Earth orbit to lunar orbit, and then also what we would need to land it, which meant that we needed to design a customized purpose-built lander just for this habitat alone. And then once we got it down to the surface, we would need a certain set of equipment to be able to transfer it from the lander down to the building site. And so all this, you know, all these different elements and features were part of the architecture that we were putting together. Next slide. And everything really started with the discussion about how we could use what we knew, which was a lot of architecture around the ISS. And the ISS, these are mostly, you know, metallic structures, isogrid type pressurized vessels with added thermal and shielding for impact on the outside. And so we wanted to take a close look at this architecture, learn from that technology, and try to also implement or think about using new forms of structures that have already been tested by NASA and have actually been deployed on the ISS through Bigelow. So these were inflatable shell type technologies. And if you go to the next slide, we took these two we married the structures, and we started to look here at, for example, how you could take this idea of a woven mesh and discretize it or break it up into different elements around the geometry and integrate that with other elements, hard elements like airlocks or metal structures or windows, because this is all part of part of the challenge of working with woven mesh structures, is how do you integrate these with rigid elements. If you go to the next slide. And this is an image of the hybrid structure that we designed in its compact configuration. You can see here in the illustration, we're trying to illustrate how you would take this this habitat, pack it, tie the shell inboard, and then protect it with a fairing before preparing it on the launcher. If you go to the next slide. And so here are some of the mission components that we took a close look at. The first one is the habitat service module. So the habitat service module actually supplies power to the habitat when it's in transit, because when it's in transit, it also needs to supply energy for maintaining the right temperature for the life control systems. If it gets too cold or if it gets too hot, these life control systems, they have a lot of sensitive hardware and computers. So that needs to be, in a controlled environment. The other element is the airlock module, which was not part of the habitat architecture itself, but actually external. And so we imagine that having an airlock module would be more beneficial as an outside element, because then you wouldn't bring dust into the habitat module, or you can at least mitigate how much dust it would bring in. The other element is the tug, and the tug would also have to be designed and sized for the habitat mass, because the tug would take the habitat from low Earth orbit and push it all the way to lunar orbit. The launcher, again, we talked about using various vehicles, but the SLS was the architecture that we went ahead with. And then the lander, which was also one of the biggest elements, because you need to take that large habitat structure from lunar orbit down to the surface. And of course, there's a lot of fuel involved, in which actually makes up the majority of the mass. And so that's something that we had to consider. And then once you have the habitat in place, you also need a power station, some form of energy to be able to power your architecture and your infrastructure. And we looked at two types of power stations. One was a nuclear fission reactor, and then the other one was an array of solar cells. And then finally, external radiators. You need to be able to reject heat that's being generated inside the habitat, because you have a lot of equipment, you have people, producing heat, and you want to be able to get that out of the habitat, because it has to be a very controlled and comfortable environment. If you go to the next slide, please. And then here you see an illustration of how we imagined these elements being launched into orbit and then to the surface of the moon. You can see the first launch would take the habitat into low Earth orbit. The second would take the tug, and then finally the lander. They would rendezvous in lunar orbit, and then from there the habitat would be landed on the moon. If you go to the next slide, please. And here are some additional illustrations showing how we imagine the sequence of events taking place. We actually worked with a really amazing animation company to put a video together. So these are still shots from that animation, but you can see that some of these elements are already pretty detailed. But the focus of this was to try and illustrate how you would take the habitat from this large lander, which would deliver the habitat really high up above the lunar surface. You would need a crane, and the crane would have to take the habitat down to some kind of a platform that would then be pulled by a vehicle to its final destination. And that's where it would be assembled and deployed. If you go to the next slide, here's an image of what that looks like. And so for crew accommodations, again, we looked at the ISS for volumes, trying to understand how much volume you would need for a mission duration that we had targeted. And I think the key was that we wanted to make sure we had no less than 25 cubic meters of habitable volume per person. But we also wanted to, understand what the implications of living on the moon would be, because it's different from a microgravity environment. On the moon, you actually have gravity, and so you still, you have to deal with friction. You have your movement is very different, and you also have a wide range of spaces that you want to accommodate inside of this multi-purpose structure. And so, after looking at various iterations and really studying, what the best net habitable volume for the mission architecture would be, we landed at somewhere about 80 cubic meters per person. And if you go to the next slide, here are just a list of the different human factors that we started to consider. So things like visibility, just being able to locate what it is you're looking, where you're going, or being able to identify equipment when it needs to be like fixed or upgraded, or just having proximity to computer screens and making sure that you can see as much as your surroundings as possible for communication. Lighting was another big factor. We wanted to introduce this idea of controlled lighting so that you can not just provide task lighting, but also simulate and even recreate some of the natural conditions that you would have on Earth, like the sun rising or the sun setting, and having those kinds of environmental factors in there. And then physical mobility, cognitive performance is another one in acoustic materials, looking at different materials for acoustic performance. If you go to the next slide. And here's another list of different kinds of human factors that we looked at. So again, volume is a key element here. Accessibility, making sure that you can mobilize your body from one location to the next. In our case, we had a vertical structure, and so it was important to be able to move vertically through the structure. And the crew quarters also, we wanted to centralize these spaces because we wanted them to be as private as possible, but also communal. And so there was a key kind of design decision there in how we distributed those spaces. Mechanical equipment and storage and supplies. This is another factor which you see in these images, that there's things all over the place, where in our design we really try to emphasize the need to locate a lot of mechanical and storage in locations where it's accessible, but not doesn't actually impede your mobility or just your focus on what it is you're doing, so that you can put these in certain locations behind panels. If you go to the next slide. Here's an image illustrating how we thought about daylighting. So this is pretty typical for how we approach design, but I think it's really unique in this case, because if you think about electric lighting is always there to supplement natural lighting. We always want to use natural lighting as something that's the kind of like the main driver. But when you're on the moon, obviously natural lighting is a real challenge, and so you have to find ways and opportunities of creating these rhythms, these natural rhythms. And this could be done through locating lighting on various surfaces below, at eye level and above you. If you go to the next slide. This is a breakdown of the different volumes and how we started to distribute the spaces. You can see that the structure makes up about 20% of the volume. Circulation makes up about 10% of the volume, and that the central spine that you see in the middle, where you were actually able to move through the center of the structure to get from one floor to the next. Storage and compartments. A lot of this was happening at the perimeter, so we chose to put this at the perimeter, but also in between floors, where you could locate things like mechanical and other supplies. If you go to the next slide. This is an image of the working level. Again, you can see that we really tried to optimize the amount of volume that people would get, but lighting is a key feature here, which you see distributed throughout. Lighting on the floor for path, for path lighting, lighting in the ceiling, lighting on the walls, just really trying to maximize the amount of control that you had over illuminating different working surfaces. If you go to the next slide. This is an image of the crew quarters. So in this case, we approached the crew quarters as this kind of integrated pod, so that every crew member had their own integrated pod with all of the features that they would need for entertainment, for personal time, for just storing personal materials, but also that there would be the ability to open up into this common space where everyone would gather to prepare for their day or to do the work that they need to do. If you go to the next slide. Here are some drawings of how the geometry works. So you can see everything is placed at the perimeter. We really try to emphasize the central space. All the panels that you see on the floor, these are all meant to be accessible. But then there's this central core which defines the circulation space. And the geometry definition at the bottom, this really helped us understand, how this shape was being created and generated. And this had a lot to do also with looking at the material that we were working with, which was that interwoven mesh. If you go to the next slide. This is a section through the module. You can see here how the spaces are broken up. So from the ground floor, this is where you have, it's more of all of the working equipment, things that you need to prepare for exiting the module for EVAs. And then also, a place where you can repair your suit, where you can do exercise. So, very heavy activities. And then the second floor, this is where you do experiments, where you have laboratories, biological experimental equipment. The third floor, this is where the crew quarters was. And then finally, the fourth floor, where we tried to locate a kind of garden where you can produce your own food for helping offset some of the life support system requirements, but also to help you just have access to vegetation. If you go to the next slide.
So further on in trying to develop the design for the environment that it's going to be in, outside of Earth's protective atmosphere and our magnetic field, there's really three types of radiation that you have to contend with. There's the solar wind, which is a constant stream of charged particles, which is pretty low level, and it takes a little bit of matter to stop it. There's also galactic cosmic rays, which are the same type of particles, but generated in supernovae. So they travel throughout the universe at near the speed of light. And being on the surface of the moon is one good part of that, is that you're protected from half of them by the body of the moon, but it's really hard to stop them. And then there is solar flares, which, depending on the solar cycle, every once in a while, the sun spews out a bunch of a lot higher level of particles. And the good thing about these is that they're predictable. We do have a suite of satellites that are monitoring the sun constantly. And because these travel relatively slow compared to the speed of light, one gets about an hour or a little bit about over an hour of warning, and they do pass by pretty quickly. So they don't happen very often. So the strategy for defending against those are to just have a hardened part of the habitat where the crew can shelter for a little bit while they pass. And so here, these are the solar particle events, and then galactic cosmic rays.
If you go to this slide, maybe I can add to this. These are excerpts from the NASA requirements, actually ESA and NASA requirements. And these are the limits for different age groups. And you can see on the bottom that they have different limits depending on what age you are. And this has a lot to do with your the potential to develop cancer-related illnesses as you get older. But the limits are being reanalyzed right now. So this is pretty old, but I think we'll see that depending on the destination, because these are designed for microgravity, the low Earth orbit. Depending on the destination, these limits could potentially change, and they vary for different industries around on Earth. So this is really interesting to understand and study. There's also some available software that you can consider using as you're doing some of these studies. There's, for example, open source software like Alteris, which is a NASA developed software. You can query their available materials list and look at what you're actually building, like in terms of assembly and thicknesses, and that can help you understand how much radiation you're getting through all that material.
And so the CDF team built a special model using our geometry and the way we laid out all of the storage and materials and tested different ideas for shielding. One was to propose, the one that you will see illustrated is to build a sort of a regolith wall around the base, which could serve as your sort of shelter for hiding from the solar particle events. Maybe a little bit more radiation protection is if you actually bury the habitat partly, but that makes it challenging from a standpoint of connectivity and access to the surface and things like that. So there's different ideas you could do of how to protect the habitats, the inhabitants from the radiation.
And this is a cross section through one of the windows / columns. And I think maybe we mentioned this at the beginning, but the column is integral to this idea because essentially it's like an exoskeleton that wraps the structure, and the mesh, the deployable mesh, is supported by that. And so this is trying to capture that detail. And when we worked on the geometry for this model and the CAD model that you saw before, we actually started to layer each one of these layers discretely to provide ESA with the ability to apply a material attribute to each one of these layers. And you can look at, for example, the list on the left, which goes from on the exterior, which goes from structure to thermal to radiation. Initially what you have the external protective layer, which protects against dust and impact. And this is in the form of a material product called Nextel AF62. And then following that, you have the multi-layer insulation for thermal control. And this is made up of a series of multiple layers, a combination of double aluminized mylar and Kapton. And then you have the MMOD fabric layer on the inside for redundancy. And then finally, another layer of foam. And all this is outside of the structural layer, which is that woven mesh, and that's helping support the atmosphere on the inside. Then on the inside, you need the bladder. So the bladder is what contains the air. And then following that, you have some additional materials for protection and for people to interface with. This is very important because you want whatever the crew is exposed to, you want that to be safe for the crew to use. You don't want it to have too much outgassing. And then finally, we came up with this idea of adding an internal wall layer on the very inside. And we had, various ways of putting this, locating it on the crew quarters, locating it wherever people spend most of their time, because it would be a heavy, a lot of material to add, and it would weigh down the structure. But we wanted to, locate this strategically, and that's an idea for anyone thinking about how to mitigate radiation. Water is a really good material for that. If you go to the next slide. Part of the CDF study also included life support systems. And again, we learned a lot from looking at the ISS. And so you see that image on the bottom right. This is the old configuration for life support systems, but you see starting from the left, at the very end of that picture, that's the shower. Then you have the toilet. These are all inside of typical ISPRs, which is the rack system that the ISS is using. And then you have the oxygen generation system and the water recovery system. And more recently, actually, if you go to the next slide, ESA has been working on more advanced life support systems, things that even supplement, for example, food production, because it's something that's going to be very important in the future. So in our study for the, for producing oxygen, we went with this system called the Advanced Closed Loop System, which you see on the bottom right with one of the ESA astronauts. And you can see that it's made up of these two racks, and it's much smaller actually. So it looks like, technology is getting smaller and smaller. And we also thought about using, for example, this Melissa photobioreactor, which was supposed to supplement some of the food requirement by 5%. And what you see there is you see the photobioreactor producing this food called spirulina, which could be consumed by the crew. And maybe in the future, you can have more advanced, plant chambers, but of course this would require some pretty large equipment to be able to support that kind of food growth. If you go to the next slide. And then finally, just to talk about the power, this was something that's very important because as soon as we identified how much power that habitat required, which was a power requirement of 59 kilowatts, that's just one habitat. we saw that the power station was, extremely large, because you have all these solar panels, you have a lot of the substructure. You would have to, assemble these on site. It's a lot of work to do. It's possible you could do that, and it would definitely be more in line with self-sufficiency. But we also have the option of using a fission reactor system, which weighed a lot less than the solar power station. And when we sized the fission reactor compared to the power station, the fission reactor was actually about 5.6 metric tons compared to the power station, which I think was more like 15 metric tons. So it was a big difference. And the other thing about the solar power is that it has to be strategically located. So you have to, place it well above ground. It has to have high exposure to sunlight. You have to be able to track the sunlight. It's a pretty complex system that you would need. You're not talking about your typical solar panels that you put on the roof, on Earth. That's it.
A little bit about the structure, and to give you a sense of the challenges of designing the enclosure for these habitats, is that on Earth, as architects, we mostly support our buildings to stand up, and a typical gravity load on a floor that you're standing on some floor right now is usually 2 to 5 kPa. Maybe 10 if you're designing a library or some heavy storage. Compare that to the challenge of containing 1 atmosphere. So 1 atmosphere at sea level is about 100 kPa. So 10 to 20 times more force than just supporting a floor on Earth. And one strategy is that, well, okay, we have humans that live high up in the mountains, and if you take the biggest cities on Earth that are really high up, for example, Potosi in Bolivia is a sizable city where the atmospheric pressure is about 60% of sea level pressure. But even then, you're still talking about an order of magnitude more force. And so that is why all of these space structures are some sort of form of a cylinder or some sort of curved structure that contains the air pressure in tension as much as possible. So having flat surfaces on a pressurized vessel is really, really difficult. And so that's kind of like, it's not just futuristic looking things and why things look bulbous or cylinder-like in space. And again, looking at the inflatable shell, by definition, a thin membrane carries all of the load in tension. So it's super efficient in containing the pressure. We try to be more creative with the exact geometry. So this is a study for one of the pedals where we use some plugins for Grasshopper and Rhino in order to compute the exact shape that the membrane will take given the boundary conditions. And here we studied the tension, and just kind of to show that we got the right shape, right? If you develop some kind of a complex shape and you apply a pressure normal to it, if there's no moment, that means that it's carrying all of the load in the membrane, actually in the plane of it, so you have the correct shape. And then to constrain it, you still need during launch, for example, and transfer and landing, besides the atmospheric pressure, you still have a lot of dynamic loads from the launch, which can go up to 3 to 5 Gs for human rated rockets, up to 10 Gs for non-human rated rockets. And so it still requires a rigid shell, which we sort of decided to place along the perimeter and create this 3-pedaled design. This is key because it leaves the center space open for the architecture that Daniel described already. I think this is a quick little rotation of what the structure could look like.
And just to summarize, I think overall, what we designed here is really focused on habitable space. And so the habitable volume was, I think, about 390 cubic meters. And then we had a habitable area of about 100 square meters distributed between the 4 floors. But what you see there is you need to project those floors outward to be able to get that extra area. And yeah, I think we really tried to integrate as much technology into this design process as possible. And at the same time, we were also talking to an astronaut, Jeffrey Hoffman, who was working in tangent with us to think about how we can make this more human-centric.
This is some of the ideas of once you get there and you can start experimenting with using the local resources. So one thing they could easily do is build this protective shell around the base floor. Once you have the module in place, they will give you extra radiation protection against solar flares. And remember, at the South Pole, the sun is always along the horizon. So all of the radiation from the sun comes horizontally at you, not from above, like we're used to here in mid-latitudes on Earth. And then this is sort of a vision in the future. We designed the first habitat, but the whole idea of being there is that as you live on the moon, you learn how to build architecture for the moon better. And so this is sort of an idea of how in the future you'd experiment with locally constructed habitats to help the moon village grow.
And so in 2019, this is when we actually first got invited to the Biennale, which was supposed to take place in 2020, but that got postponed to 2021 because of the pandemic. But the invitation was to bring this idea of the moon village to this large event, and that would bring a lot of architects from around the world, and at the same time, get others thinking about future societies in space. And so the theme of the Biennale was to imagine how we were going to live together and to rise to new challenges, new societal challenges. If you go to the next slide. So we went to the site. This took place in 2020. And you can see that there were a lot of possible locations, and this is right next to the water. This is there's actually like a large shipyard, which I think is unused, but whenever the Biennale comes, this is where they bring a lot of equipment. And this whole area here was supposed to be in a large park installed with different pavilions from different architecture firms. Georgi, I forgot what is the name of this area again? It's called the
Giardini di Biennale.
Yeah, the Giardini di Biennale. And so you can see here in this image, this is our selected site right next to the water. And so we were actually asked to bring this large scale pavilion, which would be a mock-up or architectural mock-up of what the Moon Village habitat would look like. If you go to the next slide. And you see we had to customize this for for Earth conditions. So we included this large door at each pedal. We also put the staircase. We engineered this to actually work really well for Earth, but the idea was to try and simulate what it would look like on the moon and feel like. If you go to the next slide. And one sort of innovation that we wanted to use on this pavilion and use it as a test bed is to experiment with different ways of additive manufacturing. I'm sure all of you in school are familiar with 3D printers of various sorts, and even NASA has been in the last 5 or 6 years through their 3D printed challenge, trying to get people to think of how we could use this new technology out in space. Most of the stuff that people are familiar with in 3D printing is printing using polymers and these little prototypes that are quite fragile, and people are starting to invest in new ideas of how to do more durable materials. Like Daniel mentioned, we have this project, how to 3D print in concrete. And we're thinking that for outer space, some kind of a metal would really be a good idea. And so when you think about it, welding is exactly what 3D printing is delivering a little bit of material and adding it over time. And so if you take a welding torch and attach it to a computer-controlled robot, then you could have 3D printing in metal, in steel or aluminum. And we partnered with this company MX3D out of Amsterdam,
that does exactly that. They have a series of ABB robots where they deposit, weld one layer at a time, and de facto 3D print in stainless steel. And recently they've gotten a lot of press on this bridge, which they built and have exhibited a number of times. So you might have seen this. They recently actually installed it on a canal in Amsterdam, so you can actually go and visit it there yourself. And so we took this idea and see how we could apply it to our floor system, right? It's still, when you 3D print, the different layers have different properties, whether you're doing along the deposit length or across the deposit beams. And so we figured that probably for an internal structure, it would be really good. It's still a lot of, there's still a lot of technical challenges to work out how to contain the pressure, but the internal floor would be a perfect target to do 3D printing. And so we took the support points for our sort of 3 vertical frames and applied this form finding software to figure out where the best place to put material is. And it kind of runs a little bit like this, where it starts with the floor and then does this iterative process where it kind of gives you a guide of where the materials is. Obviously, this is not ready to print as it is the material that you get out of the computational software. So we went through a series of steps to rationalize this into something that is, more uniform. And oh, Daniel, you want to talk real quick about then? We had to kind of adapt this to the process.
Yeah, definitely, because also we had limitations coming from the robotic manufacturing process itself, and that really helped us drive the way that we were interpolating the geometry from the analysis model. Because the 3D printer, if you imagine on that top image on the left, as you're printing vertically, the more inclined you are, the less adhesion there is from one bead to the next. And so the incline was limited to 35 degrees. What you see in that diagram is us trying to basically illustrate how every single member has an incline of 35 degrees or less, so that we can make it as printable as possible. Otherwise, you could have some imperfections in the 3D print, or it could just fail altogether. But we developed some tools to help us articulate that geometry and the topology.
And then, we had to study, we had to study how to adapt the floor to make sure that it is printable within the reach of the robot. So this is sort of the sphere that the robot can reach around and print it. So we tested this before starting the prints. And then we had to develop a way to take the 3D printed geometry and marry it with the floor finish, which was supposed to be glass in this case, obviously not for the moon, and connect it to the rest of the structure. And so we came up with this frame to make it fit around it. We obviously studied it and engineered it over several steps to make sure it's absolutely the lightest possible. This was designed for 1G to be used on Earth and for assembly loads. So it's actually a lot bulkier than what you would have for the 1/6G with only 4 crew members up on the moon. This is the rendering of what the floor would have looked like. And these are little few images of what the material looks like exactly. You see the different layers of the beads and the type of cool shapes and you can come up with to transition from one element to the other.
It was also, it's not only the overall geometry that you want to optimize, but also you can even see on the picture on the left, the cross section, you want to get that angle to be as close as possible to the limit, if not less. So it took us a lot of, like crafting the geometry over several iterations to get the topology to be just right.
And so the MX3D actually 3D printed the whole floor for us. This is an image of the final on the floor, all of the 3D print geometry for the all 3 pedals. Unfortunately, COVID put a wrench in our plans, and so we have a lot of the pieces of the habitat fabricated, but our general contractor kind of pulled out at the last minute, and so we could not put the pavilion together. But we did retool our exhibit, so we do have a model of the whole habitat, and a pretty big model of one of the individual units with one of the petals taken out. So this is out in Venice until end of November. If anybody here, if you guys are there, you're welcome to go and visit. But then we at the end we sort of reconcentrated on producing a video that Daniel alluded to, that I think we'd like to show you at the end to conclude, basically telling the story in a few minutes. And let me see if I can bring it up.
Yeah. And this was a collaboration still with ISA, with Jeffrey Hoffman and with the team members from SOM.
Can you hear the sound?
You have to enable sound, the options above.
Yeah.
Then maybe you can make it full screen.
More than 50 years have passed since humans last traveled to the moon, and there's still much we don't know about the brightest object in our night sky. What would it mean to return to the moon today? To leave more than flags and footsteps? To create a sustainable home? It would open new avenues for science. It could kickstart an outer space economy. And it would allow us to create a new kind of community, to discover how we might live together beyond the Earth. The European Space Agency's concept for a moon village is an international endeavor, bringing together governments, industry, and perhaps private entrepreneurs to support a permanent human presence on the moon. If an earlier era of space exploration was driven by competition, this one will be defined by collaboration. What would it take to truly thrive in space? How could we make the moon feel like home? Built from a rigid composite frame and an inflatable structural shell, the habitat maximizes usable space and creates a sense of openness on 4 levels. The first phase of development will allow crews to live, work, and continue building the settlement. Gradually, additional infrastructure and equipment will arrive, and new habitation units can serve functions such as food production and science operations. Eventually, the Moon Village will grow into a thriving community, a hub for science, exploration, and even tourism. Visible from everywhere on Earth, the moon has always given humans something to aspire to, a place to set our sights on. And soon, it will be a place we might call home.
There you go, November 21st is when it closes. So that's kind of the story that we have about our vision of the Moon Village. And I think, Sandra, we can take some questions now.
Okay, great. Thank you very much. What an impressive presentation. Very great. So please turn your cameras on and get ready for the discussion. We'll start with the first question by Franziska. I told you, Georgi and Daniel, that many of the students have not been in touch with space architecture before, and some have, so you will see different kinds of questions. Franziska, please.
Yes, hello. Thank you for your great presentation. And you kind of answered my question, but I will ask it in addition. So my question was, how important was for you the analysis of the target group and who will live and use the habitats? And did you also talk a lot to astronauts about how they, let's say, imagine their perfect moon habitat? And was this a very important part of the design process, or because I kind of imagine that you get overwhelmed of all those technical restrictions and all the things you have if you plan on the moon, and maybe you then kind of forget about the people you are building for, because usually on Earth this is kind of the most important factor, or one of the most important factors if you do a design. So what do you, or what is your experience with that?
Yeah, that's a great question. I think from the very beginning of the project, even before we had an idea for what we wanted to emphasize the study on, by that I mean focusing on the habitat itself, we did solicit a lot of feedback from various interested, folks at ESA, outside of ESA, at NASA, at different conferences. I remember attending conferences like the ISDC conference. There was like a few Moon Village conferences. I remember just talking to different astronauts, even talking to, for example, Jeffrey Hoffman, he was a big part of the project, and getting his feedback was really priceless. We took a few trips down to MIT, where he's a professor, and we talked to him about the concept as it was evolving, getting his feedback. It was very important to us to make this an open, like an open source project. It was very much about trying to bring as many ideas as possible to the habitat. We even talked to experts in deployable shell systems, like what you see here. We talked to a few companies who were actually building structures out of this material. Unfortunately, we couldn't bring them on board because it was cost prohibitive to interact with them at that technical level. But we did get to work with ESA experts on identifying what the right materials were for certain aspects of it. So yeah, it was very open, very open, very collaborative. You saw that there was a wide range of experts giving us feedback, everything from life support systems to thinking about crew accommodations. And so there was a lot of interaction with people outside of the SOM design process. Yeah.
But just add that you, I think, alluded to one thing of how architects can contribute to this, because obviously people have been flying in space for a few decades now, and people have gone into this environment, but almost everything that's flown so far is, started with the rocket, and you have a bunch of requirements of what the rocket is, and then you put the spacecraft in the rocket, and that has a bunch of requirements, and then you put all of the systems in the spacecraft, and the last thing that kind of tries to fit is the human. And that's part of the reason why astronauts have to train so long, is that they have to adapt to all this machinery that's keeping them alive. And so this is fine, sustainable for when you're going for a few weeks or even a few months. But if you want to live longer, you have to bring this type of thinking that we as architects have, is where you start with the human and you figure out what they're doing and what they need, and then try to add the technology to support what the humans want, rather than trying to think of it the other way around. Obviously, you need both directions, because it's still very difficult and very dangerous. But there's this extra level type of thinking that we as architects can bring and hopefully implement pretty soon.
Yes, stunning project. Thank you very much.
Thank you, Franziska. We will also have another talk on this social, psychological issue of living in extreme environments. Next talk is by Alma, please. Our next question is by Alma.
Hello, thank you very much. Thank you very much for
nice
this.
to see you again.
Nice to see you too. I hope you're well.
Yes.
I am actually going to Venice in 2 weeks, so I will be seeing this project in person. So I'm looking forward to it. My question would be, what kind of radiation protection did you plan for the windows? And also another question, is there also some materials from Moon that you would use for building?
For the windows, you would need to place some kind of a shutter. It's something that actually we didn't design for the habitat itself, but it's something that you would need, like the shutters that you see on the cupola for the ISS. And those would need to provide protection, not just from radiation, but also from impact, because the windows would be a weak point, right? And then in addition to that, we also thought about using the regolith. The regolith itself as a material could be used to create enough density to protect you from radiation. I think you would definitely have to build up a large structure if you wanted to protect from complete radiation exposure. But if you limit your duration, so if you limit your mission duration, you can actually reduce the amount of materials that you need. And for special occasions, like when you have a solar particle event, you could create a storm shelter that could be internalized inside the habitat, where you have additional material, maybe things like water, or even like some kind of a like a polymer type material. Anything with a lot of hydrogen is very useful. Or even there's new types of metals like boron infused metals, which are being used for spacecrafts. But I think you definitely want to have multiple layers of radiation, multiple types of materials, because I think one of the key takeaways from a lot of the research that we've come across is that it's not just one material that helps, but you need to look at unique ways of combining materials to help create that radiation protection.
Mm-hmm. Thank you.
Yeah.
Thank you very much, Daniel, for this talk, for this answer. It's also on Earth like this, right? There's not one material that can do all. And especially in an extreme environment, it would be nice to have this flexible, malleable material that can make big places and protect from everything, but that doesn't happen. But following Alma's talk, and because we are working in the design studio on the ISIU on the Moon, have you looked at other materials except the regolith to use for in situ resources?
I mean, the main reason to go to the poles is because you have water, right? That's the rest of the moon is so dry. I've heard this analogy that if you find concrete lying on the moon, it would be useful to mine it for its water. So if you have the water on the South Pole, you can do quite a lot of things with it. You know, if you split it with into hydrogen and oxygen, get your, you know, oxygen. But if you bring some carbon from Earth and maybe some nitrogen, you can build quite a lot of you know, polymers out of that pretty easily. We didn't look into that too much, and again, we chose to work, you know, develop the master plan of how this could grow, and then concentrated on the first habitat. So one thing I'd point out is that in this 4-level design, since it's the first habitat, it has to have everything. So it's the only one you have. But the idea is that as you add more of them, just like on any village or any city on Earth, you start to specialize. You could have one that's just for living, one that's just a lab, one that's just storage, one that's just experimenting, and that a big reason for going there is you could learn how to use all the resources there and experiment with things like that. This would be like one of the main activities we envision is figuring out what to do with the resources on the moon and learning to live there.
There's also various ideas for how you could do 3D printing or construction with regolith. I think you could, for example, there's a lot of metals in regolith, and so if you had the right tool set, you could extract metals to create reinforcement. And then the byproduct of that would be something that you could use in large wall structures, or you could even use it for berms or roads. There's another way of also 3D printing. You could bring some kind of a binder with you, but the binder would also, you know, you would have to ship it. So there's a cost implication there. Or you can just use direct energy deposit, which is more like welding or even microwaves. But one of our experts, Advinit Makaya, he really knows a lot about this. He's an expert in advanced additive manufacturing, and he's talked about these different ideas to us before. But in the study that you see here, we didn't use a binder. We were actually thinking about using direct energy deposition to be able to create these large vertical structures like the wall that you see in this picture here. But for the roads, you could use microwaving, or you could use a binder. Again, it's just, there's different technologies, different ways of approaching this problem. I think you could, you could dig deeper into this if you wanted to and find what works for your concept.
My thinking is that anything that doesn't involve containing pressure could be a target for in situ resource utilization, but the real challenge is making pressure vessels, because as I showed, the forces there are much bigger than anything else, and any of these 3D printing techniques still have a ways to go in order to build a pressure vessel. But anything that's inside, for example, the floor structure, anything that's not holding pressure could easily be a target for manufacturing on the moon using either the polymers or the regolith or other things.
Thank you, Georgi and Daniel. I think this is a lot of an answer for now. Probably we will have more questions as are you later. Sebastian, the next question is from you.
Yeah, the question is if we actually start kind of living on the moon far in the future, or when we start these projects, how soon do we have to think about like things like how to deal with dead people, and will there be graveyards on the moon, or will we send them back to Earth, and or landfills? What will we do with waste and garbage, and or will there be churches or kind of spiritual places, or or prisons?
No.
Maybe even where if people become criminal?
Very good question. Well, I mean, most missions or all missions that are flown now are sort of this quasi-military arrangement where you have a commander and there's like a strict set of rules of how everybody's behaving. I personally think that in as you grow up, go longer, you have to have some kind of a blend where if there is an emergency up on the moon, is a lot more deadly than you have here on Earth. So you have to, in an emergency, you have to have some structures to make sure everybody acts fast, and speed is of the essence. So you do need some kind of a rigid hierarchy in an emergency, but obviously for day-to-day life, you would need something a lot more democratic. So I'm always thinking that maybe it'd be some kind of a blend of two. Another thing is not just dead people and bad people, but also children is a fascinating topic to discuss. You've never had a family go up there with kids in space, so that is something that we'd like to think. But I think part of this would be answered by being there, right? If just like here on Earth, when we've sort of expanded into new frontiers, the way that the first settlers didn't really provide all the answers, but it did set a tone for it. So the best I think we could do is set up the first sort of community and give it the right type of an example and a right master plan, and then hopefully that will guide people as they figure out how to live there. About daring, I think I would leave the people there, right? If you'll be your body will probably survive on the moon for billions of years if you leave it there.
Also, human spaceflight is transforming as we speak. I mean, you've seen the news, you've seen that there's been civilian crew now with, there's a lot less, I guess, like requirements for a civilian crew. They're just going out there to explore, to, have an experience. And I imagine that if you were to, take this step by step, that low Earth orbit would require some of these new facility typologies, for not just for tourism, but also for new forms of experimentation. And so if you build this first around Earth, then you could take a leap to the moon, where it's much more difficult, it's much more dangerous. But over time, you would require completely new typologies of architecture to facilitate different activities. And so like the activities that you listed here, it's maybe it's like really far out there, but it's still something that you would have to take with you if you're building an off-world society.
Okay, thank you. I have just another very quick question. Is it possible to store food just in the moon atmosphere? Can you just put it outside and because there's no air, it doesn't, you can store it like that?
That's an interesting thought. I hadn't thought about that.
Where does the food come from?
Well, I mean, here everything comes from Earth in this first one. Again, that's one of the other things that eventually people would grow more and more food there. But the one thing is that outside on the moon, the temperature swings extremely. There's no atmosphere, and so when the sun is shining on something, it heats up to hundreds of degrees, and then on its shady side, it's minus hundreds of degrees. So anything that you leave outside temperature would fluctuate up and down. If you leave it in, sorry, go ahead. Huh?
No, I was just saying, food is a hard thing to imagine storing in an unprotected environment.
You would be able to permanently in shadow. Sorry.
Yeah, I think you could store equipment, for example, like even sensitive equipment inside of like a regolith built structure. It doesn't have to be pressurized or conditioned. You can imagine doing that, storing some devices that you need for doing like civil engineering. But food is I think that one's a hard one. Yeah, I think you need a special, some kind of special storage facility for food. You wouldn't just be able to put it out there.
Okay, thank you.
Yeah.
Ichu, the next question is from you.
Yes, and my question is, will the construction waste be generated during the construction and the use of these habitats? And how long the survey life of this habitat? And if it's not permanent, what will you do with these constructions? at the end of their life circle, like sending them back to the Earth or something?
I can maybe just take a stab at this, but I think like at the beginning of the presentation, you talked about, creating this large master plan for different, almost like land use, right? Land use strategies. So there's definitely going to be waste. You want to be able to protect some of the environment, and you want to have a plan for where you place the waste or how you use the waste. Minimize waste as much as possible. But I think the idea of building an off-world society, again, is to be as self-sufficient and sustainable as you can be. And it's something that we're learning how to do better and better today on Earth, right? I think it's definitely something that will happen. Even though we're designing these habitats on Earth, engineering them and building them on Earth, to get them there will require some form of construction as well. So there will be some waste from that. In the design of this one habitat, the service life requirements that ESA had given us was 10 years. I would imagine that would want this to survive much longer than that, but that was the minimum requirement that they had put in the CDF study. And then what you do with the end life of a habitat, that's a good question. I think you could repurpose the habitat. Obviously, if it survives longer than 10 years, you can repurpose its function. So rather than being something that's multi-use, that you could maybe use it as a very specific function, like food production, or maybe doing more like experiments. But over time, you would want to find ways of reusing some of the structures. But that's a great question, because it's something that we deal with even on Earth, like how do you repurpose existing structures in an urban environment when there's so much building stock around the world? Do we just continue building new structures, using new materials, producing more waste? Or do we find more intelligent ways of repurposing what we're designing? And that's part of what we do as well. We find ways of creating, like an end of life strategy for our structures. And that has more to do with like life cycle analysis and how we design. Yeah.
I think that's last point about end of life is key, and I think that's one of the big benefits of thinking about architecture in outer space and what actually living on the moon can teach us and help us back here on Earth, is that when every molecule that you take, you have to account for, because it's so expensive to get things there. You have to really think of what's the use of basically every atom that you take there, right? Moving atoms from one place to another in the solar system is very expensive. And so you have to account for, every gram of matter that you take. And so it really focuses the mind to minimize waste. And the concept of waste might eventually, hopefully, stop existing, because you would account for every molecule that you take. And, which we keep talking here in architecture on Earth about creating a sustainable future for humanity. But the construction industry still has an insane amount of waste, which you can get away with here on Earth because it's so cheap moving material from one part of the planet to another, relatively speaking. But when you have to account for every gram of stuff, I think eventually we will learn how to use every molecule and you'll have no waste. So that's the goal. We're obviously very far away from it here on Earth, but maybe our next generation of architects will make better than the previous and minimize construction waste. But it's a challenge, and I think it's something that space architecture can really contribute to in just the whole endeavor of sending humans to space.
Okay, thank you.
Edis, the next question is from you, please.
Yes, thank you for the presentation. I think most part of my question is answered. I just wanted to know if there is some simulations available to you that can tell you exactly how thick the wall should be to stop, let's say, 70% of radiation in those worst case scenarios of supernovas. So something just like we have here on Earth, the ways to calculate exactly how much centimeters do we need for thermal isolation, and maybe that can save the material and have the prognosis of exactly how long can the astronauts stay in the habitat.
I think Daniel mentioned that. Oh, sorry. Go ahead.
Oh no, if you want to take this one, go ahead.
Well, Daniel mentioned that there are some software available from NASA. I think Daniel used one on our recent project that we're doing right now, a follow-up, where you could set the thicknesses and the material properties, and it calculates the radiation transmissivity. One thing is it's a little bit the data in the databases behind it are not as well studied as the example that you brought up when you're trying to compute U value and thermal transmissivity. Those are very accurate. I think the science is still a little bit not as accurate, and we don't have as much data as materials here on Earth.
Okay.
I think I forgot, Daniel, what the CDF study, they used some other software. Do you know what exactly software they used to do the radiation study?
Yeah, actually. So the challenge here again is the mission duration. So that defines, your radiation limits, because you're still going out into an environment where you're going to get some radiation exposure. And I think so ESA actually used a few different software tools. The first one was Alteris, which was more of like big picture, defining materials and what kinds of radiation they would expect. And then when we got into the more detailed CAD model, they were using a software called FastRad. And FastRad is typically used for satellites to be able to protect instruments and different hardware within the satellite. But they were using this software, and what we discovered was that for our mission duration, which was somewhere between like around 300 consecutive days, we needed, for solar particle events, we needed 40 centimeters of regolith surrounding the habitat structure, at least at the ground level, in addition to everything else that we talked about, which made up the external assembly, plus the water shielding. So it's a lot of different materials, a lot of radiation protection. But if you want to increase your mission duration, you need more material. If you decrease it, it's different. But also it depends on, what is the strategy for this moon village? Do we imagine, society being built outside of Earth, exposed to this radiation for many years? Or is it more about like cycling people, bringing them back and forth from Earth to the moon and maybe giving them an experience and developing science and technology, but not letting them stay there for too long? So I think that's the open-ended question, is that defines the level of danger.
Okay, thank you. I will definitely check Altaris. Thank you.
Yeah, FastRad is you would have to buy it, but
I just need to register with Altaris, so I will try with that one first. Thank you.
Okay.
May I add something? Because I think there is no... Engineers always want an exact number, right? So the first question is, how thick has the radiation shielding to be? What material should I use? The problem is there is no answer to that. And as Daniel said, everything is a matter of trade-off. And what is the goal? So at the moment, I think all the calculations are made for short or medium-long trips, because long trips are just not calculatable, right? The thing with radiation is it's something that adds up to your body. That's why children are not allowed, to be in the hospital or something. And also astronauts have a lifetime kind of on board the ISS. So after a certain time you spend in high mountains or in the International Space Station, the risk is increasing in order to get these diseases that are related to radiation.
Yeah.
For example,
and
I mean deaths, but later.
Yeah. So the radiation coming from the sun, the solar wind and the solar particle events, those are in the range that you can deal with them. You know, as Daniel said, you need you can't put 40 centimeters of regolith up in orbit, but on the surface of the moon or Mars, that's pretty straightforward to do. The thing is that the galactic cosmic rays, there's really nothing you can do about them. I think you need a meter of lead to stop one of them. And being on the surface of the moon or Mars, that basically the planet hides you from half of the universe. But really, galactic cosmic rays are you can't really stop them. It takes all of the Earth's magnetic field and all of the atmosphere to stop most of them, and they still get to the surface of the Earth. That is really like a lifetime accumulation of galactic cosmic rays exposure.
Yeah, like what you said,
the universe is trying to kill you. Sorry.
No, I just like what Sandra said about this being a trade-off. So if you're just defining your own mission objectives, then this is something that you have to think very carefully about. But if there is like already like a mission objective set out for you, then you have to find ways of working with different materials and different strategies. There's no one solution to this.
Thank you.
Thank you, Edith, for this question. Philip, next question is by you.
Yeah, I have a question regarding the 3D printing of metal. And you said it's basically like welding, but wouldn't you need an extremely high energy output and therefore a lot of resources to 3D print metal? For example, with welding, you basically have to melt the metal, and in comparison with printing with plastic like PLA, the energy you use to melt the material is far less. And couldn't you just weld, bend, fold the metal into shape and have the same results?
That is a good question. So it is basically welding, so that is energy intensive. The idea is that with the 3D printing of the metal, you could really reduce the material to the absolute minimum. You could start with plate material and cut it out, but that's another way that very often you do sort of optimized structures is these really spindly structures. But then the way usually that's manufactured is that you start with a base material and then you cut things out of it, which then you have a bunch of waste as well that you then go and remelt. I think for sending 3D printed structures to space, I think it's worth it, because there you can really, any sort of gram of matter that you save pays in dividends, because it takes so much fuel and energy to get it up there. I think 3D printing in metal on the moon would be challenging, because right there you're limited also by the amount of energy you have. But theoretically, if you have a few nuclear fission things, you would have extra energy to 3D print. I think the metal is good because it's ductile and pretty forgiving. A lot of these 3D printing plastics are more brittle. But that is a good, interesting trade-off study to whether for the again, all of this is for the pressure containing elements like the floors or walls. I think 3D printing in some plastics might be an option too. We wanted to, for the Biennale Pavilion, we wanted to use the opportunity to explore this new technology and see what we could do with it. We actually did a lot of experiments with MX3D. we had a very different strategy for 3D printing it in the beginning that was not working out, because it does have a lot of heat, and so there's a lot of residual stresses of it. So we were printing things horizontally, and they were all warping and things like that. So we did learn quite a bit of how to use the technology as well. So that's kind of partly why we were interested in the 3D printing of steel.
All right, yeah. Thanks for the answer.
No problem.
Do you really use steel or an alloy?
It was stainless steel. I guess, yeah, so alloy, but yeah, stainless steel.
Katharina, next question is by you.
Yes, first of all, thank you for the really nice presentation, the visualization you showed us at the end. It basically answered my question because I couldn't imagine how life would be there if you be able to travel around the different habitats. And because you talked a lot about radiation and how important it is to have like a shielding. I'm like quite new to like lunar architecture, so I wasn't sure how the astronaut suits allow you to like travel around and move freely like you used in like a normal village. And I mean, if you're there for 300 days, I think it's quite important that you can move freely. So yeah, but I mean, in your visualization or in your movie, you showed that it's meant to be that you travel around and like exchange with the other habitats. So yeah, I think it's basically answered.
Yeah, I mean, the idea is to
that...
move inside pressurized stuff as much as possible, because an EVA it still takes some preparation. It's not like here on Earth, you grab your coat, your keys, and you head out. You have to pre-breathe and things like that. On the ISS, because the ISS is pressurized at sea level, 1 full atmosphere, and the spacesuits are at, I think, quite low pressure. I think 30 or 40% of that. And so you have to prepare for several hours before you actually go out in order to pre-breathe, right? Because whenever you change pressure, your body reacts. That is another benefit for pressurizing your habitat, not at 1 atmosphere, but at some lower percentage of it, because then the difference between the inner pressure of the habitat and your spacesuit is lower. And so you could do an EVA with far less preparation and stuff like that. But it's not like you can, hop on and get out. It'll still take, many minutes or an hour to prepare to get out, even in the best of circumstances.
I was going to add one thing that the visualization just barely captures is that in the planning of the modules, they're all interconnected. So there's a series of tunnels that connect every module together. So the idea was that you don't necessarily have to go outside to go to another adjacent module, but that you go outside only when necessary. And all that, is planned ahead of time. But you have the ability to move between the modules through pressurized protected tunnels. And I think that's key. You want to be able to create an infrastructure of interconnectivity so that you can limit exposure to possible, hazards and things like that.
Thank you.
Thank you, Katharina, for this question, and thank you, Daniel, for this input. This will be an issue also for the people planning a lunar base, how to get around. Thank you very much. Inside, from inside to the outside and between the modules. Yeah, it shall be easy, quick, pleasant, and at the same time not take too much volume. The ultimate challenge, right, for the architect. Marcel, please ask your next question.
No, thank you for your presentation. It's very interesting. I was wondering, the vision video said that cooperation, that we need cooperation instead of competition, comparing like the competition of flying to the moon, probably between Soviet Union and the US. And I think in the ISS, it's all like right now, there's a lot of cooperation between like all the countries, and that's working very well. But how would that be ensured in this kind of idea where it's also maybe tourism and more people and so on? Like did you have concepts for this, or did you mainly focus on the architecture, like on the concepts for the architecture, or did you also have ideas for these, I don't know, living together concepts, or maybe concepts for how do we really cooperate in these projects? Like, for example, who would pay for this, and then who would be the person basically in charge for the project, or whatever, like these kind of questions.
You know, it's kind of like what's happening with the ISS, where you have all these discrete elements, you know, different technologies coming together as a part of this large assembly, but these are being developed by different nations, and there's different agreements happening between these different countries. You know, even though NASA is often kind of seen as the leader in a lot of what's happening out in space with human spaceflight, they're working very closely with other space agencies like ESA, you know, and ESA contributes a lot of different assets and expertise to the ISS. So cooperation is just something that needs to happen. There's no one entity or country that has the ability or even the money to do this alone. You have to work collaboratively, because you also want to develop new technologies. You know, I think when you look at this design, especially, we're not looking at a large, for example, like a large envelope or a large structure that is all encompassing. We're looking at a lot of individual discrete elements and technologies that are coming together to create this infrastructure. And as soon as you start to break apart all these different technologies, you'll have different players, different companies, different agencies working on these technologies who actually have specialized in these technologies, who can bring it together, you know. And I think that's just cooperation is going to happen naturally in that way. Whether you force it, whether you want it to happen or not, it's going to need to happen through various agreements, and that's part of the Moon Village concept as well.
The big question is, will it involve China or not? Because China was, you know, specifically kept out of the International Space Station, and they have a very, very ambitious goals themselves that are carrying out. They just sent a crew to their new space station last week, I think, for a long duration stay and things like that. So any potential competition would be not with the Soviet Union or Russia, but with China in the future. So if some kind of a collaborative endeavor could happen with them, I think it'd be very beneficial. And the ISS pulled it off. I mean, for me, the miracle of the International Space Station is the technology and the design and everything is phenomenally difficult. But putting together the international agreement with so many partners that for so long to cooperate on such a complex project is probably the first in history. And it's the people, you know, claim it's the first peacetime or the biggest and most complicated peacetime collaborative project. And even if the US and Russia are at each other's throats quite a bit recently, they're still, you know, cooperating and living together on the ISS. So it's as a symbol itself and as a organizational achievement, it's phenomenal. It's out of this world.
Yeah, and this is not a question of like, I guess, economics, but for anything to be sustainable, any kind of human activity, whether it's development on Earth or in space, it has to be economically viable. And that's one of the key factors in thinking about, you know, how you build up infrastructure. Like maybe one good example in the US is a company like SpaceX, where, you know, I think we've understood that they're very vertically oriented or structured, but they depend a lot on cooperation with NASA, with other companies to help develop and deliver some of the hardware that they've been known for. And so even a company like that, where, you know, you imagine SpaceX can take us to the moon, Mars on their own, it's actually in collaboration with a lot of different entities.
Thank you, Daniel. Georgi. Alspetta, please.
Hello. Thank you for the presentation, first of all. And my question is regarding to the art and design of the habitat. Because I was wondering if, since there are so many factors on the moon, like the radiation or the air pressure, if there was still any space left for design
or if everything is kind of shaped by this its function or these factors, or also if there were some plans for putting some pieces of art inside, or even art in any kind for the crew, maybe some musical instruments also or something, because we had a lecture from a scientist who was in the polar basis on the South Pole for 1 year. And it sounded that it was quite important to him to have some personal objects with him there. So that's my question.
Yeah, we put a guitar in here.
That's a good question. I think going back to the question about the design, this is still very, it's very schematic, it's open-ended. I think we can imagine configuring the space in so many ways. That's part of I think the structural idea is that we liberate the space in the middle so that you can make use of it in any way possible. And that's one of the key, I think, fundamental ideas here is if you have an idea for how to reuse some of the space or reconfigure it, you can do that. And we wanted to give the users also the ability to customize their space to some extent. So that's important, I think. Yeah.
And on our next project now, we're also exploring ways of using different types of materials on the inside for the finishes. So it looks warmer and feels cozier on the inside, so you can play along with it a lot. But maybe one point is, as long as it's not containing pressure, everything else is actually more liberated on Earth, because you need a lot less structure and you have a lot less flexibility in to 3D print, as we talked, or to do something really crazy.
Okay, thank you.
Cheers.
I have to add something, because I think it is really necessary. We need all those issues. We need to be crazy. We need to be room for making things that are not wanted or not expected. So I've just posted this Space Oddity by Chris Hadfield in the chat. I think it's one of the nicest.
That's a groovy video, yeah.
But even 1 week before, we had a film team on board of the ISS. So I'm sure we will see some nice videos from them as well soon.
And there's a second one going up soon too.
Yeah, it's becoming a normality.
That's a space arts race, right?
The space arts race, yes.
We'll film the first video in space.
It is.
Anyway.
Okay, we have a question by Lali, please. Thank you, Aspetter, for this question.
Yes. So I wonder about the purpose of the project and the future realization. When can we know and say that the project can be the project is ready to be carried out and can be launched, and who validates the project, and how can we test and be sure that the functioning of these units, and can we be sure of this?
Yeah, the first one is a really hard question, because I think the purpose of the project was to bring together a lot of different experts who are interested in this big picture idea. Everybody who's an expert is always focused on one aspect of a certain technology. And when you give everybody a target like this, when you give somebody a vision that drives all these different capabilities and different skill sets, it gives people a target to build on. And the purpose of the project was really just to inspire and to help, give everyone around the world an indication that there's interest in this, that there's a lot of possibility to make this happen if all the right collaborators come together. And obviously this would not be taking place near term, but I think we studied a lot of really unique opportunities here. And that's what we wanted to introduce to the thinking behind space architecture. How can you master plan? How can you design a habitat that would be multi-purpose? How can you integrate all these various technologies? And what would it take to bring all this together? And then who validates this? this would be validated by government agencies, by manufacturers, contractors working on different technologies. This would take a lot of testing. It's very expensive to validate these kinds of technologies for human spaceflight, especially when as soon as you introduce a human element, things get very complicated, very complex, and you would need to, for example, just the shell and the metal frame interface. That's something that would take a lot of investment and rigorous testing to ensure that it works. You don't want to design something like this and just build it and send it out there. What we were trying to do is just demonstrate that there's unique opportunities for combining these different ideas together. And then the last question was, how can we test and be sure, or can we be sure it's working? Yeah, you have to be sure it's working before you send it out into space. So some of the missions that go around the moon, they're uncrewed first. They would be uncrewed, like the Orion missions that are upcoming. Those go uncrewed. They send the vehicle out there, without people. They make sure that all the systems are working, that everything is operational. This same thing here. You would have to deploy this and send it out there without people. And then once it's tested and working, then you bring in the people. And that's just part of the equation. Yeah.
Thank you very much, Daniel, Georgi. We have no time left anymore. I'll ask one last time for the students of the ADU, if they would like to ask a question, then you have to shout now. And in the meantime, we have a lot of questions in the YouTube chat.
Yeah, I have one question.
One moment, Marcel.
Yeah.
We have Masha here, Florian, Huta, Surrounded, Albert Rakuma. Hello from Houston, Daniel, Georgi. So thank you for the talk. Hello, thank you for this informative and inspiration presentation. My question would be, is it realistic that the first expeditions to the moon will have such sophisticated and comfortable habitats? So we have, Marcel, what is your question?
I was just wondering about in your project or in these kind of projects, are there also like philosophers and sociologists working in these projects, or like what kind of disciplines besides architects and engineers are involved in these planning processes?
Okay, maybe let's make this the roundup. Right, Georgi and Daniel, maybe you say something about the state of the art and how we wish it should be, right? Something like this.
I think Daniel alluded to it, that we try to get as many different opinions and different types of people. I don't think we've engaged professional philosophers per se, but definitely very various types of experts in all sorts of different fields. It's definitely a very collaborative endeavor that you need a lot of different inputs on. Sandra, maybe we can answer later can you send us the link to the YouTube page and I can write down answers there or something? That might be.
Yes, that
we
would
can
be
do that.
lovely. Okay.
Great.
So that means if any of you has an urgent questions, please put it in the YouTube chat. Georgi Petrov and Daniel Inocente will answer them. I thank you very much to be part of our module today. And yes, go forward with the next phase of your Moon Village project.
Thank you very much.
Thanks, Sandra.
Thank you.
Thanks, everyone.
Bye.
Good to see you all. Thank you for the questions.
Thanks.
Thanks, bye.
Bye. Thanks.
Thank you. Bye.
Thank you.